Good morning and welcome to this next lecture on vibrations of plates and shells. We are in the force response section. So, the next force we are going to look at it again, a line force, but this time it is at an angle to the coordinates. So, how does it look like? We have this plate, X, Y, Z, this is B, and the force is now at an angle. It is a line force, uniform magnitude, but it is at an angle. Okay. So, there is not much of a difference, except that one thing you have to keep track of, that is this. Let us say this direction is L, okay, and let us say F star is the force per unit length. So, F star into L is the total force. Okay. Now, if we were integrating along this direction, then whatever integral 0 to L, then F star dl would give me the full force. Okay. But in actuality, when I compute from my Q3, my Fmn, when I compute, what do I get? One of the integrals is 0 to a dx. It is an integral along x. Okay, integral along x. Integral along x. Okay. Now, if I integrate along dl with this force per unit length, I get F, but I am going to integrate over a shorter length in the x direction. Okay. And I have to recover the full force F. Okay. So, something here dx should actually give me F, but 0 to a is a smaller length. Okay. So, what should that be? So, what I have, and let us say this line is y equal to px, it is a line going through origin hypothetically. Okay. Then I have integral along L direction F star into dl is equal to integral along L F star square root of dx square plus dy square. Okay. Now, dy is equal to p dx. So, dy square is equal to p square dx square. Now, suddenly what happens? I am going to integrate along x, f star square root of dx square plus p square dx square, which is what? Integral along x f square square root of 1 plus p square dx. So, this augmented force along the x direction is equal to the f star along the L direction. So I need this much a factor over here to keep my amplitudes correct. Okay. So now it's pretty straightforward from here. So my Q3 x comma y comma t looks like f star square root of 1 plus p square and delta y minus px into e to the power of j omega t. Okay. So this is per unit length, this gives me one length, I have force per unit length. Okay. So what is my Fmn star, okay, which I use when I remove the e to the power j omega t. Okay. So 0 to a, 0 to b, f star square root of 1 plus p square delta y minus px sin m pi x by a sin n pi y by b dx dy and 4 by rho h a b, that we can't forget. Okay. So now what happens here if I do the y integral first. So I get 4 pi rho h a b, we have to keep the x till the end. Okay. 1 plus p square and this becomes sin m pi x by a sin n pi px by b and dx. Okay. So these are constants, they come out. Okay. Then I can represent this as a sum of two causes or difference of two causes and I can proceed. Okay. One last step, 4 f star square root 1 plus p square by rho h a b sin integral 0 to a sin m pi x by a sin n pi px by b dx. That is my Fmn star. So from here I move to gamma tilde mn and all that. Okay. So that's one more. Now let us see the next one is a moving load, a moving point force. Moving point force on a simply supported plate. Okay. So what do we have? We have the plate again. And let us say we have a moving load. Okay. So we will keep it downward. Okay. Normally you do it on a bridge. Okay. You have a bridge and you have a truck moving. So that is the idea. Okay. Truck moves on the bridge. Okay. So let me keep it downward. This is my x, this is my y, this is my z. Okay. So my Q3, so this is not a harmonic situation now, it is not a harmonic force, it is going to be a transient and we have to deal with like transient like that. So my Q3, where do I do cubes? Q3 of x comma y comma t is equal to the force, I will put a minus delta x minus x star, then delta of y minus y star, but now this time y star is moving, okay, y minus Vt. Okay. So I have to restrict it actually on the plate, okay. I have to restrict it on the plate, so I have to put a Heaviside function that restricts it from y0 to, okay, yb, okay. Notionally it has to be there, okay. That means it is valid as long as the force remains on the beam, on the plate, sorry, okay. So now what is my Fmn of t for a, this is a transient case now, it is integral 0 to a integral 0 to b minus f delta x minus x star delta y minus Vt sine m pi x by a sine n pi y by b dx dy and 4 by rho h ab. So this now looks like 4 by rho h ab with a minus, put a minus here, then sine m pi x star by a into sine n pi Vt by b. Okay. So now Fmn is a time dependent term, not harmonic. Okay. So now I have eta mn double dot plus twice zeta mn omega mn eta dot plus omega square mn eta mn functions of time is equal to this Fmnt. Okay. So now you have to use Laplace transform and do the convolution. Okay. So Laplace transform and convolution. I have given it in the right in the beginning. Okay. So then what else? So the next one is a line moment. Okay. I am just giving you all ideas. Line moment on a simply supported plate. Okay. So geometry is similar or same. We have a plate. Let us align the line moment with the dyadic in the this direction. Okay, that means going like this, back and forth. Okay, here is my z, x and y. So this is pretty straightforward. If the total moment is m, then I can have m divided by b. If this length is b, then I have delta dash x minus x star. Okay. Then h to restrict it from y minus 0 to h y minus b, and this is e to the power j omega t harmonic. Okay. So, this moment is force into length, this b gives me one length, this delta dash gives me length squared. So, I have force over unit area, force over area. So, units are also okay. Okay. Next is an impact. An impact on a simply supported plate. Okay. So, again the geometry, x, y, z. Okay. Suppose the ball, a mass of m coming down, it has a velocity v1. Okay. But going up, going back up, it has a velocity v2. v1. Okay. So, now the final is m v2 k, the final momentum, minus the initial. Initial is minus m v1 k. Is it, therefore, the change is m v2 plus v1 k. Okay. So, that is the change now for the plate also with a minus. Okay. So, now suppose this happens, this interaction happens over delta t, over a time delta t. Okay, something like this. The change in momentum, okay, happens over a time delta t. The interaction is over a delta t. Okay, this is delta t. Okay, then I have minus m, and this v2 plus v1, I will call it v bar. Okay, then h t minus t1 minus h t minus t1 plus delta. Okay, that is the momentum change. Okay, that is equal to the force into delta t. Okay, impulse is force into delta t, that is equal to the momentum change, right. Force into time is impulse, which is equal to change in momentum. Okay. So, what is my F now? F is equal to minus mv bar h t minus t1 minus h t minus t1 plus delta t over delta t. Okay. So, as delta t becomes smaller, this fellow starts off a step at t1 and this drops a step, okay, back to 0 at T1 plus delta t. Now as delta t starts to become smaller and smaller, this line comes closer and closer to T1, but I have a delta t in the denominator also, so this becomes minus mv bar delta t minus T1. It becomes an impulse. Okay. So what is my descriptor now? This is the force. This is the force descriptor. Okay. So I have Q3 x comma y comma t is minus mv bar delta t minus T1, and let us say the impact is over a point, all hypothetical situations, x star delta y minus y star. So this is a actual mass, okay, to velocity length over time. This gives me 1 over time. Okay, this is force itself, okay, mass into acceleration, then this gives me a length, this gives me a length, so total is a force per unit area. Okay. So now if we actually try to find the transient Fmn t, that looks like minus mv bar, okay, 4 by rho h a b, the delta t minus T1 sine m pi x star by a sine n pi y star by b, okay, and then we have, so this is Fmn, okay. So now if that goes into my eta mn double dot equation, this is Fmn of t with a delta function, okay. So if initial conditions are 0, then my eta mn of t is 1 over gamma mn integral 0 to t, this thing tau, which is minus mv bar 4 by rho h a b with tau as the argument, delta tau minus T1 sine m pi x star by a sine n pi y star by b, okay, then e to the minus zeta mn omega mn t minus tau sine gamma mn t minus tau d tau. Okay, and if T1 happens to be less than t, then we will get 1 over gamma mn minus mv bar 4 by rho h a b, okay, sine m pi x star by a sine n pi y star by b e to the power of minus zeta mn omega mn t minus T1 sine gamma mn t minus T1. Okay. So that is the eta mn. Then the response is double sum eta mn phi mn. W. Okay. So you can more or less see that this is an oscillatory function and this is a decaying function. So the response will be somewhat like this, okay, oscillating and decaying. Okay. Per mode, for every mode it is like that. For every mode that is contributing, every mode eta mn is a single mode. Here we are summing up a mode. So if we look at it mode by mode, then there will be some constant in front, there will be an oscillation in time, then a decay. So this will be, every mode will decay like that. Okay, so that is your impact. Okay. Now so this more or less covers the type of forces that you can see. I mean there can be a lot more types of forces, there is no limit to that in some sense. Okay. You can have a moving car and further oscillating load, etc., etc., okay, so on and so forth, rotating moving moment, etc. You can go to any extent, but this gives you a good idea of the type of normal everyday forces you can encounter and how to model a force and get a response. Okay. Now we have to look at response of curved systems also. Okay. Response of a curved shell. So response of a cylindrical shell. To a point force. Okay. Now, so let us say this is my cylinder, okay, this is my cylindrical shell. And somewhere I am applying a point force, somewhere I apply a point force. Now the point force descriptor, point force description is also different when you have curvatures. Okay. So what you should get is integral over the area of this structure delta alpha minus alpha 1 star, alpha 1 minus alpha 1 star, delta alpha 2 minus alpha 2 star, then you get A1 d alpha 1, A2 d alpha 2. That should be equal to 1. That should be equal to 1. Okay. So now if we have a cylinder where this is x minus some x star, this will be theta minus theta star, and so A1 is 1, d alpha 1 is dx, A2 is a, d alpha 2 is d theta, okay, that has to be equal to 1. Okay. So now what would be my delta descriptor? The delta descriptor will be delta x minus x star, delta theta minus theta star by a. That is my delta function in cylindrical coordinates. In rectangular coordinates it was delta x minus x star, delta y minus y star. Okay, but in cylindrical coordinates it is this, where a is the radius. Okay, so that is the first point. Now The other point is this. Let us call it the point 1. I wanted to make. The other is this. We are going to look at a simply supported shell. Simply supported shell. Cylindrical shell. Now, we have seen this before when you have theta coordinate and closed in theta coordinate. Okay. So, this is my shell. If I have n equal to 3 description, then it looks like this. Okay. So, these are the, let us say, 0 displacement node points, this is node points, and these are the maximas, maxima, 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 maxima and maxima. Okay. But now if I oscillate this N3 at its own some natural frequency M3T, then these points will permanently be nodes, right. These points will be permanent node, they will be permanent antinodes. But what about if there is a displacement here? That cannot be modeled if we stick with just this picture. So, there has to be a rotated picture also. Okay. So, there has to be some kind of a rotated picture which talks of peak here. Okay. I do not know how that goes, whatever. So, there has to be a rotated picture, slightly rotated picture. Okay. So, now, in order to incorporate that rotated picture, we will need 2 sets of modes, 2 sets of modes. We need 2 sets of modes. Okay. So, for the simply supported shell, cylindrical shell, UXMN, one set is cos m pi x by L cos n theta, U theta mn is sin m pi x by L sin n theta. Then U3mn is sin m pi x by L cos n theta, but the other set is cos n theta plus pi by 2n sin n theta plus pi by 2n and cos n theta plus pi by 2n. So, this gives me the rotation. I need cos n theta plus pi by 2 sin n theta plus pi by 2 cos n theta plus pi by 2. Okay. So, we will keep it a minus, actually we will stick with a minus here, as the textbook sticks with a minus to be consistent with the text. So, minus, okay, minus n theta minus sin n theta minus cos n theta minus pi by 2. Okay. So, this gives me cos n theta cos pi by 2 plus sin n theta sin pi by 2. So, sin n theta. So, the other set here is sin n theta. This gives me sin n theta cos pi by 2 minus cos n theta sin pi by 2. So, this is minus cos n theta, the next set, and here I get the same as before. So, I get sin n theta. Okay. So, the other, so this is the first set, this forms the first set. Form the first set. The other set is cos m pi x by L sin n theta, sin m pi x by L cos n theta with a minus in front, then sin m pi x by L sin n theta. Okay. So, you have these two sets of modes, okay, and they are orthogonal. They are orthogonal in cos and sin, they are orthogonal. Okay. So, we will look at that next time. The time is up here, we will close. Thank you.